The ASME dimensioning standard has a set of fundamental rules for dimensioning, with the goal of making it so that there's one and only one way of understanding each feature and dimension. And I've given you a handout in a PDF with these rules. Look at all that. And I've also given you a translation, the simplified language. So we'll just go through these one by one. The very first rule is pretty important. Each dimension shall have a tolerance. And the reason for that is there are no perfect parts. There are really precise parts, but no perfect parts, and every dimension must have a tolerance. You can put the tolerance directly with the dimension, like this, or you can put it in the title block, or you can write a general note. This rule translates to, well, there are several things. First is, do not scale the drawing. So you have to give them every dimension they will need. With some exceptions about scaling off the drawing, a company that makes wiring harnesses will make this drawing full scale and not put dimensions on it. They'll glue it to a sheet of plywood, and the assembler actually uses physical clips and strings the pieces of wire on here, and so they might scale from the drawing. Or something like a template used to install a sink. This doesn't have full dimensions, and you can scale off this drawing. This same rule basically says never assume anything. That's a key idea. So, for example, in this gasket drawing, we cannot assume that this thing is symmetrical and centered. We cannot assume. We must specify exactly where everything is located. Remember drawing this part? In the original version of this isometric drawing, this 0.25 was omitted, and I added it back in because we cannot assume that this cutout is centered. We have to know how far is it to that first dimension. This is the rule which says no duplicate dimensions. Translated. This rule says essentially a dimension should not be subject to more than one interpretation, and this will come into focus a little bit more next time when we talk about tolerancing and chain and baseline dimensioning. This one says we should not specify manufacturing methods. So here's a drawing where someone has specified to drill these holes and ream these holes. That is not acceptable. That is none of our business, how the shop makes those holes. Our business is determining what size and shape these things should be and what tolerance to apply to them. How the shop gets that is their area of expertise. And if they want to use a rat tail file and take 3 weeks to make that hole, that is their business. If you say drill, and a little bit later on the shop gets a really high-tech water jet machine that can make these holes super fast and super economically, if your drawing says drill, they would not be allowed to use that water jet. They would have to use a drill. So it's none of our concern. This is the area that the shop deals with. Then there are some dimensions you put on a drawing that are not, they don't actually have to manufacture precisely to them. These are non-mandatory dimensions. For example, let's say you do a casting drawing for a foundry, and the finished part is going to have machining, but you want the foundry to allow some extra material. That's non-mandatory. Or let's say you make a drawing of a thing that's going to be rolled in a rolls. There's a little short straight segment that comes through the rolls that you can't eliminate before you get to the round stuff. Some shops like you to dimension that straight stuff, but that is not a mandatory part of the finished loop. So you would label that non-mandatory. You don't find that terribly often. Then this rule is just pretty fundamental. It says your goal is clear communication. Well, what it actually says is dimension for maximum readability. So this is why we have ideas like the distance away from the part we put the dimension, and how far apart we put the dimension, and where we put the dimension. Our goal is communicating. This is the rule which says features should be dimensioned in the views where they appear true size and shape. This is also the rule which says always dimension to visible lines, or flip side of that, never dimension to hidden lines. This rule, this is the rule. A lot of people locally do not actually follow this rule, but the rule says when you are giving the size of wire or sheet metal or that kind of thing, you need to give the actual dimensions, the decimal size, and not just the gauge. So you cannot just say this is 10 gauge. ASME says you must also give the actual size. And their rule says you could put the gauge in parentheses after the dimension. So the reason for that is that there are multiple systems of wire and sheet metal sizes. Let's look at an example. If you were looking up what size is 10 gauge, for example. Well, if you were using American wire gauge, AWG, it would be 0.1019. If you were using the US standard, it would be 0.141. And if you were using the standard sheet metal standard, it would be 0.1345. As it happens, we use AWG for wire, like we use in electrical wiring, and we use this manufacturer's standard for sheet metal, like we'd buy at Far West Steel. So we're supposed to specify what the actual size is. A lot of local shops always use one system for one kind of product, and so they actually do write gauge. But just know that that's not actually to standard. All right, this one says if it looks like 90 degrees, it is 90 degrees. If you draw a part with orthographic views, top, front, side views, and you draw things square, then it's understood that they are square. If we did not have that rule, we would have to go through and put 90-degree angle dimensions on every single thing that was squared, and it would just fill up the whole part. So this says if it looks like 90, it is 90. Related to that are two rules that we won't really delve into here. We'll talk about them when we discuss next year in mechanical design class, when we discuss geometric dimensioning and tolerancing. This has to do with basic dimensions, and basic means theoretically exact. And this one is related. This is a implied basic zero, also involving geometric dimensions. So we'll skip over those two rules. There are several places in here where they say UOS, and that is the official ASME abbreviation for unless otherwise specified. This one, unless otherwise specified, any dimension or tolerance that you put on a drawing is understood to apply at 20 degrees Celsius, which is 68 degrees Fahrenheit. If we didn't do that, it would just be chaos, because as you know, materials expand when they get hot, and they contract when they get cold. And so what size are we supposed to use? Well, we use the size as it would be at 68 degrees Fahrenheit. And the tools we use for measuring our parts are all calibrated at 68 degrees Fahrenheit. This one you might not use too often unless you worked in certain kinds of places. Dimensions and tolerances apply in an unrestrained condition. In other words, when you put a dimension on a part, that's the dimension it would be if it were sitting on the part shelf and nobody were doing anything to it. For example, let's say you manufacture leaf springs. And if it's just sitting on a shelf, it might be this certain width. If you put it in a truck and put a load on it, it will spread out, won't it? And that dimension will get wider. But that wider loaded dimension is not what you put on your drawing. You put the unrestrained condition on your drawing. This rule says, unless otherwise specified, when you put a dimension on a feature, it applies for the full depth or length or width. So here's a rectangular block. It's 1.5 inches wide at the bottom. Remember that rule, if it looks like 90, it is 90, so these are 90-degree angles. We know that it's 1.5 wide at the top as well. You don't have to write that dimension again. Now this relates to the idea of when we draw hole patterns, we extend the center line all the way through all the holes. We connect the holes. And that lets this rule about only needing to dimension one side, that allows that rule to apply. If you did not run these center lines through here, you would need to dimension both sides and both sides. This rule applies to assemblies. So here's a picture of an old-timey desktop computer, and in the assembly it would have a hard drive. The hard drive has tolerances at the pretty much atomic level, at the angstrom level, very, very tiny tolerances. The plastic case that houses that thing has tolerances in the thousandths of an inch, maybe 10 thousandths of an inch, much bigger. So the tolerance for the housing only applies to that part. The tolerance on the hard drive drawing only applies to that part. This is a new rule in the revised standard, and it says, what it says is the dimension value does not establish a target. Here's an example, which is the best way to explain it. Let's say you give a dimension with a tolerance. You say it's 5 plus 200 thousandths minus nothing. This does not mean that 5 is what your goal is. 5 is not the target. This rule says anywhere in between 5 and 5.2 is acceptable, and none of them is better than the other. This one says if you put an XY axis on your drawing or in your digital model, it's understood that a right-hand rule applies. And the right-hand rule tells you which way the X, Y, and Z axes point. So with your right hand, the thumb points in the positive direction of Z. And this last rule is also new in this revised standard. Remember, there are no perfect parts, and so when you put a dimension on a part, it is understood to include all the bumps and dips. So the surface that you're dimensioning includes all the surface texture and flaws. And there you are. There's your whirlwind tour of the fundamental rules of dimensioning.